So hello, my name is Joey Hung. Like I said, a machine learning engineer at Progressive. I'm dealing more with the modeling MLOps sides. So we do more stuff with Kubernetes, Docker, Terraform. I'm not really a modeler per se. I've been doing machine learning for about 4 or 5 years, and I'm an engineer, so I'm clearly underdressed here today. But today I'm going to go over what model interpretability is, why it's important, going over a little technical. We're not going to do any LaTeX or anything like that. Just some quick overviews of why model interpretability is important. So being a modeler like myself, we tend to be building our machine learning models, and we have our data, we're getting our test set, looking at our test set, and if it's not, then we just kind of reshuffle it. But I think it's important to now understand what model interpretability is, and that's actually kind of important, and really should be more of a part of our machine learning pipeline and structures. So this is a really good paper that I found, and I'm going to be showing a whole bunch of papers as well of using model interpretability. So what it is, it's the degree of which humans can understand the cause of the decision. Basically, we need to know why a model made its prediction, and we need to understand that. And it's not just for us, it's also for our customers as well. So it's also known as interpretable machine learning. You may have heard of XAI or IML as well. It's been around for a while. There's lots more papers coming up these days about machine learning interpretability. And it's nice that we don't need to understand everything about parameters. We don't need to understand anything about models. We just need to know for our downstream tasks. Model metrics like A1, ROC scores, they help us, they tell us what our model is doing, but we don't really understand it. We're just getting good results, and we're kind of calling it a day. So this is a graph showing how model interpretability is becoming very important. So this is from back in 2000 going up. So more people are talking about model interpretability, and the paper's kind of going up from there. So it's getting important. So this is literally the book on interpretable machine learning, which I got a lot of my research from Christoph Molar. So he's been doing stats and also been working with machine learning interpretability for a while. So I have the link on here, share it off the slide as well, but it's a free book. It's available online, and so it's really good. So basically what interpretability is, so model generally is a black box, thinking like neural nets. They're more complicated, they're harder to understand. We don't have the ability to observe the inputs and outputs. Some models like linear regression, logistic regression, they are easier, but there are some little things where it could be a little difficult. We're going to go into that a little bit later as well. Models, not all models need to be interpreted, things like recommender systems and OCRs, basically models that don't really have a cause or an impact for a customer don't need to be interpreted. So, no one's going to die if if the Netflix algorithm doesn't do a good recommendation. So things like that. But they're also not necessary if they don't cause significant consequences. So like I said, no one's going to die if something happened like that. So those kind of models don't need to be interpreted, but they also don't need to be interpreted if they've been well studied, and they've been around for a very long time. We know how it works, and we've been testing them for a while. Things like aircraft collision detection, those things we don't need to have model interpretability for, because we've been using them for a while, and most of us are still here because of aircrafts. So we're okay for that kind of stuff. I think it is important though for especially insurance. So premiums, anything with risk assessment, underwriting, fraud detection, face detection, those kind of models that have consequences should be understood in really some way. So I'm also going to go to the reasons why we should use interpretable models. And as a machine learning practitioner, I think it's also really good for debugging. So they really help when the model can be interpreted and we can help understand what the model is doing. And as we're building our models, we have our test set, we think it's good, we ship it out, and we're saying, oh, it's actually not predicting what it is, or it's got these bad consequences, it's biased for some reason, and things like that. One example here is actually from Christoph Molar's book. He goes to an example of a wolf and dog classifier. So it's like a basic image recognition task. We have our test set, it's looking good, we're getting good accuracy, but we use some model interpretability, like heat maps where you can see where the model is looking at. This, say, one kind of model is actually not looking at the face of the animal, it can be looking at the background. So anything that's in a snowy background could be classified as a wolf. And through model interpretability, that's really going to help us understand what it's doing. Okay, cool. So another reason, I'm going to have a bunch of these reasons why I think it's important. So one thing is for building trust. So things for fairness, and we've talked about this before as well. Some of the presenters have done talk about bias in our talks. So use it for bias detection. We need to be sure that everyone's accounted for, and each group gets the same results or predictions than another. Some things are like for hiring, which is a good example. We also need to make sure there's equal opportunity for the job, regardless of race or sex, when they're at equal level. Same thing for salary. We need to make sure that it is the same when all the skills are the same level, regardless of the race. Another example is from the Compass algorithm. It actually is to predict the likeness of a criminal reoffending. It's been used in the U.S. states for like Newark, Wisconsin, California, and Florida. And ProPublica, which is it's an independent company, a nonprofit based in New York. They had investigated this algorithm through some other model interpretabilities. They found out some really like not very good things about the model. So like black defendants were twice as likely to be misclassified as having higher risk than their white counterparts. And they had actually also had stated is no better than a random untrained, is better than random untrained people on the internet. And they've also kind of fought back on this as well, saying no, it's not, because the model that he was using for interpretability wasn't exactly on par with those. So it's not a one-all be-all thing for model interpretability. One thing too, kind of going off topic here, is that the models, it really depends on your model as well. So if your model is trained inaccurate, if it's overfitting or underfitting, model interpretability may not work as well because our model is trained on different things as well. Another point we go through is going to be a couple here. So anything like face detection, ad tracking, location stats, those things should be interpretable for some way. These contain sensitive information, which can actually be tied back to the users, the place of residence, where they live, where they work, and so forth. And it helps us understand if privacy has been violated in some way. And through these model interpretability actions, we can see that as well. It also enables users to trust predictions. I recommend to take actions against privacy in the future. Another one, I'm not going to read this quote, but this is from another paper that I've read. So in doing my research, there's a lot of papers about going machine learning and model interpretability as well. One more part is for safety. This is an example in the healthcare space. So this team had studied the use of mechanical ventilations in ICUs, and basically they need to understand when they can take off a ventilator from a patient. If they took it off too early, the patient can be back on the ventilator. They took off too late, it can cause pneumonia and possibly discomfort. So they use another model interpretability system to show feature ranking and correlate it with the clinical explanations and help give confidence to the model. So what's cool, you see the thing on the right is actually showing what features are most important. And that's really what machine learning interpretability is, seeing which features have most importance for our model. So in this one, they're using this Richmond RAS scale. I'm not really sure what that means, but they had said that is the greatest feature to be used in determining when the patient should be removed off the ventilator or not. And what's cool too is that they have age, gender, and ethnicity, but it's not really important for the models. That's really good to understand trust as well, and leads to less bias because we can see from there it's not really that important. Another part is for regulation. So I'm sure many are aware that governance is going to be happening for our models, whether we like it or not, it's coming. So the EU is now requiring AI assistance to be explainable. The FTC is now prohibiting algorithms that are racially biased. The Equal Credit Opportunity Act is making it legal for companies to use biased algorithms that go for race, religion, color, sex, all that. And the Fair Credit Reporting Act is also doing it as well, where an algorithm is used to deny people employees housing, credit, insurance, or any other benefits. This is actually another thing from a vendor that Progressive's using. They're called Monitor. I'm not a paid spokesman for them, but I feel like I am because we've been using them for a while, and they have been actually helping us with our building trust in our models and doing model explainability. So Anthony Habib, he actually allowed me to use this quote. He's been mentioned in a bunch of talks as well. So he's basically saying that we need to be able to understand our models. And Monitor is a vendor that we've been using. We've been advocating for our data science to use at Progressive. So the idea is that our data scientists don't need to have model interpretability. They will be able to use it to monitor. The monitor will be able to see what's going on in the model, understand it, record transactions, do batch transactions on them as well. So they've been great as well. Finally, in the future, there's going to be some more stuff. There's going to be some more aspects in interpretability. There will be a new build coming out in, I think, next year. It's called SB 21169. And it is basically going to be prohibiting the uses of algorithms that are biased in some form or way. So it's going to be important, and it's going to come up very, very soon, I think. Now going a little more technical. Like I said, not going to be too much, but I want to go into it. Like I said, I'm an engineer, so I kind of need to. So model interpretability is really being able to understand predictions that are affecting our model. It helps us understand what the model is actually learning and justify its decisions. So you can see in this example, we have our basic pipeline of machine learning problem. We have our data, we build a model, we get our metrics, F1, ROC, RSMEs, doesn't really matter. But then from there, we can actually take that to another system. These are the model interpretability systems. And like we went through before, using trust, we can use fairness to make sure it's not biased in some way, and verify that it's actually fair in some way, and it's actually interpretable. When we have that, then I think is the next step we can set up to our customers to use. And this is all going to come back for, they'll be able to trust our models, understand what our models are doing. Same for underwriting. If, say, we predict something that's not favorable to them, even credit scores, they can go back and they can say, why is my model, like, why are you rejecting me? Oh, because of this, this, and this. Because through interpretability, we can now understand what it's doing. There are lots of methods for model interpretability. We can go from the basic ones and all the way to more complex, and we'll go from there. There are intrinsic methods, which reducing the complexity of a model. So kind of like PCA, if you've been used to that, where we're doing like a feature reduction of it and making them simpler to understand. They're using a thing called feature importance and feature summaries. Another aspect of feature summaries are partial dependence plots, which I'm showing in this graph here. This is from scikit-learn documentation on how to use partial dependence plots and showing the interaction between targets and its features. So that's a good example of how partial dependence plots are working. There are other types of methods which are intrinsic. They can also be model-specific or agnostic. Model-specific ones just using the weights directly. So like linear regression, logistic regression, we can see the coefficients and we know exactly what it's doing. We don't have to use any other systems. Agnostic is it's a black box. So the model is a black box. We only see its inputs and its outputs, and we can actually still do interpretability for that. Models like linear regression, logistic regression, those are easier to understand, and models like neural nets, SVMs are more harder. And the graph on the right kind of shows models that are easy to be interpreted may not be as accurate. So basic classic algorithms are useful. They're easy to be interpreted, but they're not as accurate. Neural nets, they're bigger, more weights, and they're harder to interpret as well. A little more about linear regression. So we can, like I said before, using the coefficients itself, and we can see that each coefficient describes the effect on the output. So if we make one change in one feature, we can see if that changes our predictions, and that's how you can use interpretability for that. It is harder though. We have larger weights, more data sets. If we have nonlinear regressions, like multi-nonlinear regressions, it's even tougher, but there are ways to kind of see that as a black box model. Logistic regression, pretty similar, but with when we're doing binary classifications. And we can also see that when one weight changes and everything's the same, we may be able to see if there is a change or not in its prediction. Again, it is possible, but there are ways to do it. Decision trees, which are like a tree structure, we can visually see like a credit aspect. If we can see what decisions the model made, we can easily see what it was trying to predict. Things with multiple decision trees are hard to understand. So maybe many trees or thousands of trees, those are kind of tougher to do. Rule-based models, so progressive, we have some if-based, some rule-based models, so just big old if-else statements. We do have these that are progressive because of their interpretability, so we need to know exactly what they're doing and why they're doing what they're supposed to be doing. They are easy to understand if we have a couple if-elses. If we have massive if-elses, like some of ours, it is tougher to use. Post hoc methods are where we're taking the model and using it as a black box. We only have access to the inputs and outputs. They're model agnostic, so we can use these things for pretty much any other model we have. We have one model that's a neural net, it's a convolution or NLP task. We can use the same model interpretability methods as we use for that model, take it to the new one. So it's nice, keeps everything kind of clean for us to use. Like I said, we only have access to inputs and outputs, so it's really great for just transferring over to new models and different features. It is useful for models that are harder to interpret, so neural nets and SVMs. They are harder to interpret, but we can use these other methods to do it. And what they actually do is actually train their own separate model to predict the outputs of this other model. So we give it all a bunch of features, we train our model, our new interpretable model sees predictions, and we're trying to predict the predictions of the model that we're working with. So one thing you may have heard of is a thing called LIME, which is for, did it go forward? Oh, yeah, sorry. Okay, cool. Sorry. So there are other post hoc methods. One of them is called, for a local surrogate model, it's called LIME. And it's literally stands for local interpretable model agnostic explanations. And they test the predictions where the variations in our inputs. And what's cool about LIME is actually building its new data set. It's generating predictions, giving our features, and making predictions from that, and generating a new data set from that. It actually, like I said, trains its own model for it. It could be linear regression, logistic regression, those type of models, which are easier to interpret. They're generally used as a local explanation, so only a certain set of features. And we can use it to make global by doing lots of predictions over lots of features. It can work for anything, data, text as well. Counterfactuals is another aspect we can use. Explains predictions by which features that we need to change to order to change the prediction. One example could be the Titanic data set. We have a person that's classified of dying. What can we change? Like their age, their sex, their cabin. And one of those features can we change to make them survive? So, like, we can say what's the possibility of them survival. Scope and rules. Another aspect of model interpretability is when we're explaining predictions by finding the decision rule. So literally, there's a line in our data set where we can see that changes that. They use reinforcement learning. They use graph search algorithms. Keep doing that to find the prediction where other features are changing, and it's literally the opposite of counterfactuals. Again, it can also work for any other model. Shapley values was really cool. One more thing we'll talk about is it's actually derived from game theory, where we're trying to predict things from a model. What's cool about Shapley values? Even Shapley is that it's actually the same unit as our predictions. So let's say if we have the Boston house data set, we're predicting the price of a house. Our Shapley values will be in dollars as well, and the predictions are in dollars. So you can really see what's important, and it's really just using that features and seeing what feature is super important. Again, it also works on any model, like all the other surrogate models, but it's expensive computationally to use. And finally, I hope this helps you understand why model interpretability is important to use. This is something that I've been working with for a while, and like I said, we've been using Monitor as a vendor to help us do this. I've been more of a developer advocate for them, helping them out, helping other customers within Progressive use it. So it's going to be important, just as training a model self. So as data scientists and engineers, we're building our models. We need to have other ways to interpret our models as well. And governance is going to be super important eventually soon. So it's not really about if, it's going to be about when. We are getting places that need governance. And models that can explain more will lead to trust, reliability, and safety and privacy. So it's going to be super important for us as well as our customers. And thank you.